So I want to talk a little bit about the design of the house and to how I came about with the design. This is not designed to be every architect's dream per se. The whole intent of the house was to serve as a home for my family. So it had to be big enough for my family, and then it also had to make economic sense, and as well as a way to teach other people the things that I've been researching with insulating concrete forms, radiant heat systems, and performance homes in general. So I had to incorporate a lot of those things into the aspects of the house. And the thing that gave itself the way out was the aesthetics to some extent. I tried to maintain some sort of aesthetic genre to make it look a little bit nicer, but overall, if something had to give, that was the first place that I had to give. Because comfort, affordability, space, performance, all of those things come first to me before the aesthetics. That said, functionally speaking, I think it's attractive enough that it wouldn't be torn down, which is the other side of the aesthetics in the function world. In order for something to be functional, it has to serve all of the purposes of its function. And for good or for ill, aesthetically pleasing is one of the functions a house performs in society. We have a sense for what a beautiful house looks like or what something attractive looks like. And if you go too far away from that norm, it becomes ugly or unattractive, and therefore its resale value goes down, and ultimately it becomes an eyesore and then becomes taken down. So even if you build a 500-year-old capacity building that can live 500 years, if it's ugly, it'll only live 50 years because it looks like garbage. The 60s had this issue with some brutalist designs that they did that people realized, okay, that's cool and to live forever, but no one wants it to, so we're going to take it down. So I've pushed as far to the boundary as I could, but hopefully maintained a little bit of the things. So, but optimization and economy in both speed and in production of the actual materials was taken into and is more paramount than the actual looks per se. So that being said, I made a rectangle. If you look at it mathematically speaking, the cost of a house is based on its envelope. The envelope of a house would be where its borders meets the exterior. So we have 5 sides of that, and technically 6 if you include the earth, which is also a good border because that also is the expensive parts. Pretty much everything in the guts of the house is relatively inexpensive, structurally speaking. You do have the costs of drywall, electrical, and finish work on the inside, which could definitely drastically change the cost of a house. But structurally speaking, we have a foundation, which is a square footage portion. Then we have the external envelope, which would be, say, the front, the sides, the back, and the other side. So those are your 4 sides, and those are a square footage calculation. And then you have the roof, which is again a square footage calculation, but on the horizontal plane. Now, if you take those things into account, the most volume you're going to get in the house, the most square foot inside relative to the perimeter outside, is a perfect sphere. Okay, a sphere has the greatest volume relative to surface area of any shape because there's a perfect radii, but it's not practicable for building a house with. So the next thing on the two-dimensional plane would be the circle. Well, a circle works and domes work, and if you look at them, they are functional, but again, they don't conform to regular neighborhoods, as well as they're persnickety to build, I would say. Not necessarily difficult, just different, and you have to account for several different things when you build with a dome. And then as well, living in a dome, they have some nuances with curves and things of that nature. Well, curves in our world are difficult to produce. It's a lot of custom work when you get into curves. So the cost of curvature is very real. And so we have predominantly adopted straight wall systems because of cost efficiency, because we can make materials straight and make boxes and stuff much easier than we can curves and things of that nature. So from an economic standpoint, the most economically feasible house is a perfect square because you're going to maximize your interior floor area relative to your external surface area. So it takes the least amount of walls to create the most amount of space. Well, that only exists up until a point because our materials have a limitation on how far they can span. So if you go much past 28 feet or so, you can't go full span without load-bearing walls. So then your structure inside becomes much less variable. My ideal in a house is if you can have no interior load-bearing walls at all, and everything is externally maintained, so that way the interior can be infinitely reworked without touching the external envelope. Now, I didn't have that option on this house because I needed to go wide enough to give me the space I needed to account for the 2-car garage or 3-car garage. I consider it a 1.5-car garage, but to give that much space on the main level, as well as a walking space, and to account for the roof system to be able to span the whole way, it needed a little bit more support because I'm 37 feet wide. And trusses to span 37 feet, it would be extraordinarily tall. They're already taller than normal. But those are some of the economic factors of when you're looking into building a house. If you go too far wide, you're having to worry about supports in the middle. And in order to, the most economic house would probably be a 30 by 30, and because then you could span the full 30 both directions, trusses, first level, second floor, and you can make an 1,800 square foot house with no load bearing interiors, and that would maximize your square footage relative to the external perimeter. I did close to that, but I am now 37 by 65. In the next video, I'll talk about the ICF specifically, of how I optimize the ICF.